Hi everyone, our speaker today is Enhao Liu, and he will talk about some invariants by intervals and essential covers. Take it away.
Thank you very much, Teresa. Thank you for introduction, and thank the organizers for inviting me to this AATRN network to give a talk today. So today, I will talk about my recent works about studying the multi-parameter persistence. First of all, as a self-introduction, so my name is Enhao Liu again, and now I worked as a program-specified researcher at ASHBI, the Institute for the Advanced Study of Human Biology in Kyoto University. So today's talk is based on the recent work, the joint work with Hideto Asashiba and Etienne Gauthier. And you will see if later you see two names that is our recent paper name titled Interval Multiplicity of Persistent Modules. And if you see three names, that is another paper named titled the Interval Replacement of Persistent Modules. Okay, great. All right, let's go to the first page. So first, let me just briefly review the TDA and the main tool called the persistent homology in TDA. So we know that TDA is a mathematical theory for studying the shape of data. You want to distinguish different shape of data. And the classical one-parameter persistent homology is one of the main tools in TDA. So let me just briefly review the persistent homology, one parameter. For example, we assign with the input data in Euclidean space, say, the input data that just finite points, the set of finite points, which we are called the point cloud. For example, in this case, we are assigned some 6 points in R2. And then we want to build the so-called Bohr model with respect to this data, this point. In a sense, so each point becomes the center of the closed Bohrs. And the radius of each Bohr is the parameter. And we increase the parameter and we get this nested sequence of topological spaces, as you can see in this picture. And then, of course, we apply the homology. So normally with field coefficient, and we get the so-called the sequence of vector spaces, k-vector spaces. And this is later I will formalize it, but now so this sequence of vector spaces connected by linear maps. This is actually some algebraic object, and by decomposing this algebraic object, we have the so-called barcodes or persistent diagrams. So they're just the building blocks of this algebraic object, and so each bars or each intervals, as you can see in this picture, they represent the lifetime or they track the cycles appearing in this filtration. Yes. Yes, so I think everyone know very familiar with this one parameter persistence. And later I will formalize again the persistent homology and persistent module by using the language of replacement theory. So in practice, we will also encounter such two-parameter filtration case, which we call the bifiltration. So as you can see, so now the filtration is controlled by like multiple parameters. Like in this figure, it is controlled by the radius parameter horizontally, and vertically it is controlled by the cardinality or the density of the points. So basically it's controlled by multiple parameters. So this is why we call multi-parameter persistence. Or generally we can think that the filtration, such filtration is indexed by some other poset. As you can see, the one parameter filtration is indexed by some totally ordered poset. So now we will formalize it in the next page, page. So now I'll introduce persistent homology and persistent modules from the perspectives of representation theory. So in this talk, we always fix field K, and we use mod K to denote small mod K to denote the category of finite dimensional K vector spaces. And we always use boldface P to denote the finite poset. And also, finite poset can be naturally regarded as a category in the trivial, I mean, in a Euro sense. And then, what is a filtration? So filtration is nothing but just a functor from this poset as a category to the, say, category of the topological spaces. We call it the p-filtration. So as an easy example, as we saw before in the previous page, in the one-parameter filtration case, so the poset P can be taken as a totally ordered set with 5 elements, 1 to 5. And so in this talk, we always visualize the finite poset by the directed Hasse diagrams, or sometimes we call the Hasse quiver. Anyway, so any sense. So it's just a Hasse diagram of a poset, but we just give the orientation of each arrows from by the rule of from the arrows always from the small element to the larger element. Okay, so we keep this convention. And what is persistent homology? So persistent homology is just the composition of this filtration with the homology functors. So again, we always fix the field K, so coefficient always K. So as a quick illustration, so here I introduce another poset, which is called the 2D grid, G52. So it's just a product of two totally ordered sets with the coordinate-wise order. So on the left is just a direct Hasse diagram of the finite poset, and this is simple animation. So as you can see, this is a filtration, right? So we assign each vertex with topological spaces, and this is p-filtration again. And then we apply the homology functor. Then we get some vector spaces on vertex and the linear maps on the arrows. So this is called the representation of this directed Hasse diagram or of this poset. Okay, so this is the composition is again the persistent homology over P. Okay. Great. So in this in our work, we always linearize. We always do the linearization of the poset category, the category poset. So we define the persistent module as a k-linear functor from Kp to mod K. So what is Kp here? So Kp is nothing but just some incident. The name is called the incidence category of P. So this category, so the object is the same as the object of P, and the only difference is the whom space. Now I mean, because we linearize, so now the whom set becomes the whom space. In a sense, it becomes a k-vector space. If x smaller than y, then it is just one-dimensional k-vector spaces with the basis pyx. So pyx is a unique element in the whom set of whom pxy, right? And if there's no relation between x and y or the relation, so the whom set is just empty set, so there's nothing. So then the linearization is just the zero vector space, the zero space. Okay, so that's all. This is the incidence category. And we denote by mod Kp the category of all P persistent modules. And it is known that because our poset is finite and also vector spaces are finite dimensional, so we have a very nice decomposition theorem called the Kurushima theorem. So each persistent module M can be decomposed uniquely by some indecomposables up to isomorphisms and permutations of order. So here, we have some multiplicity function, right? So multiplicity is just a function dm from the complete set of representatives of isomorphism classes of indecomposables to non-negative integers. So by the way, so in one parameter case, as we can see, so the multiplicity function is just the precision diagrams or the barcodes, right? So yeah, so this is the formalization. Okay, so we introduce some notations, concept about intervals, which we will focus on, we're interested in. First, of course, the first concept is about interval. So what is interval of a poset, of a finite poset? So it is just a non-empty, connected, and convex full subposet. And connected means the directed Hasse diagram of I itself is connected as a diagram, as a graph. Convex means if you take any two elements in I, and for any element z in P satisfying x smaller than z smaller than y, then this z should also belongs to I. So this is convex in the Euro sense. Okay, so we have some examples. For example, I give you 4 examples of intervals. The red regions are intervals of P. And also there's a non-interval example, like this is non-interval because this does not satisfy the convexity. And we also say a special class, subclass of intervals, namely segment. So it is just some special interval with a minimum and maximum element. So here is just minimum element is x and maximum element is just y. Okay, and we will use curly I to denote all the set of all the intervals of P. Okay, so that's the interval of a poset. So for each interval, we can define the representation or the module, the persistent module, in terms of interval. How? So for each vertex in I, element in I, we assign the one-dimensional character spaces K, otherwise 0. And for the morphisms, we assign, for the linear maps, we assign just identity map if x and y, both x and y in I, otherwise just 0. Okay, so again, so here I give you just an example of such interval module. And so interval module itself is indecomposable, so it is easy to show. And so the multiplicity of interval module, which we call the interval multiplicity, is denoted by DMVI. Okay, great. So let me first review a very classical result in a one-parameter persistence. So the interval multiplicities and the ranks, they have some relations. Okay. So for example, here I give you a filtration, one-parameter filtration, and the barcodes, and some necessary intervals for computing these interval multiplicities. First, this is well-known formula. Again, we can compute the interval multiplicity from the ranks of given persistent modules by this formula, alternating sum. And you can do the opposite way. You can also recover the rank by computing the interval multiplicities. Okay. And for example, in this case, you can see that if you look at the red interval 3, 4, the interval multiplicity is 0 in this case. Okay, but the interval rank, so the rank over 3, 4 is 2. Okay, so later I will revisit this fact because our formula actually generalized this formula, the well-known result. Okay. So almost, I'm almost introduced our first theorem, but we still need some notations. I'm sorry, this is a bit notation heavy, but let me just introduce these notations. So in this page, we assume I is a non-empty full subposet of P. So also I give an illustration of directly Hasse diagrams of both P and I. Okay. So first, this notation is very common in poset theory. So, but we use source I to denote the set of minimal elements of I, and sink I to denote the maximum element of I. With the labeling, because of finite, we can always have a labeling. So source is A1 to AN, respectively. So sink is from B1 to Bm. Okay, as you can see in the on the right hand side in the figure, you can see we have 3 sources and 2 sinks in this example. Okay. And we adopt this convention also. So the source of empty set and equal to sink of empty set is just empty set. Okay. Great. Then we have this notation, also very common in posets theory. So we have the upset of a singleton X, which is just the set of all the elements which is greater than X in P. And respectively or dually, we have the downset of X. Okay, so this is very common. And for a subset or for I, for subposet, we also have this similar notations. Upset of I, which is the union of all the upset of singletons, and also the opposite, dually the downset, okay, of I. But the next notation is not so common. So we use this double arrow to denote the proper upset. Okay, so proper upset is the upset of I and minus I, so exclude I. So for example, on the right hand side, you can see the blue region. The blue region on the top, they are express the proper upset of I, yeah, because it is outside of I. And dually, you have another blue region at the bottom that is a proper downset of I. Okay. Okay, so now if we take a pair of distinct elements in source I or dually sink I, we use this notation, the source of their pairwise common upper bound. So this is called the pre-join of A, of such boldface A. Why we call it pre-join? Because it's easy to see that because source is always the minimal element. So if this is a minimum element, so this is becomes really the join. So, but now it is just a minimal element. So this is why we give a name that's a pre-join and pre-mate. So as you can see on the right-hand side, for example, A2, A3, it has 2 pre-joins, namely A2, A3 and Y, and another is A2, A3 with subscript X. Okay, so not so this is these 2 elements, not unique elements. Okay, it's just a remark. Okay, and finally, we use the source 1I to denote the disjoint union. We connect all the pre-joins of such pair of all the pairs by source 1I. Okay, and dually sink 1I. Okay, finally, we define the so-called choice map because by definition of upset of I, so for you can for each element in upset of I, you can always find an element in a source of I that is smaller than that element. Okay, so this determines a map, a choice map. So we fix such choice later. So we use boldface C to denote the choice map from source of proper of I to source I. And we use the boldface D to denote the choice map from sink of downset of I to sink of I. Okay. So for example, you can see that A prime, we have a choice. So we choose A1 to become the smaller element in source I, which is smaller than A prime. All right, so now I think I can introduce our first main theorem. So first, we give a general formula for computing the interval multiplicities of over any finite poset, and also using the structured linear maps of the given persistent module M. And so as you can see in this the formula, so the interval multiplicity of Vi can be computed by this difference of 2 ranks of some big matrix. I will explain this big matrix later. But first, you can see that the first matrix, big matrix, block matrix, we call it, we give a name as a multiplicity matrix. So it has 9 blocks, but only 5 non-zero blocks. And the next block matrix, so it's very similar to the first one, multiplicity matrix, but just we let M3 to be 0. Okay. Okay, so now let's explain what are the entries in this formula. First, I always say the structured linear map. What does it mean? So it's just a linear map inside the persistent module M. Okay, so it just so MBA. If A is smaller than B, so it's just a linear map from MA to MB because there's a unique morphisms. So then this morphisms linear map is in a sense is unique. This is called the structured linear map of M. Okay, now. Well, first we introduce the block M1. So M1, as you can see, it has the source I as a column index, and it has the source 1I as a row index. Okay. So source I, for example, we have from A1 to AN. Okay. They are the index of the column. And for example, source 1I, again, they are just the prejoins of some pairs. So for example, here, let's look at A1, A2, W. Okay, this index. And how we define the entries inside. It's easy because we know A1 should smaller than A1, the common upper bound of A1 and A2, of course. So there's always unique morphisms from A1 to this prejoin. So we have a structured linear map from A1 to W. So this is, we put the linear map at the first entry, namely the MWA1. So similarly, you have another, because we're pairwise, so you have two columns, which is non-zero. So at the A2 column, you also have the unique morphisms, which is called the MWA2, okay? But here we give a minus sign here, okay? So this is how we construct M1. And we notice that M5 is just the dual case. So we can easily define the M5, this block. Okay. Okay, now we define M2 and M4. They are also dual, a pair of dual. And so as you can see, the column index of M2 is also again source I, but the row index is source proper of I. So here we need some choice. So here this is where we use a choice map. So for example, we fix such choice. For example, for each AK prime in source proper of I, for AK prime, we let A1 to be smaller than AK prime, for example. Then there's morphisms from A1 to AK prime, of course. And then there's a structured linear map. Then we put the AK prime A1 entry with this by this structured linear map. And other entries are zero on this row. Okay, this is how we construct M2. So similarly, we construct for M4. Okay, they are just dual, but column in M4. Okay. So finally, we have a remaining one, namely M3, the block M3. And M3, as you can see, the row index is now becomes the sink of I. So now here, so in M3, we also have a choice. So here also involves a choice. So here we only choose a pair of B1, A1 in sink I times source I, satisfying that A1 is smaller than B1. And then we put the B1, A1 entry of M3 with this structured linear map, MB1, A1. And other places, other entries are just zero. Okay, so this is how we construct this matrix. Okay, great. All right. Yes, so this slide is just explaining how our formula is really a generalization of that well-known formula. Maybe if I have time later, I will revisit this page, or I will put this in the Q&A session. If you have a question, we can revisit this page later. Okay, so let me just skip this page. So let's see an example in a 2D grid case. Let's see another poset example. For example, if we take P to be such 5x2 grid, and we take the two sources, two things, interval I, for example, this example. So again, I just write the formula down here. So in this example, as you can see, so X here is just a join. So there's only unique pairwise upper bound. of A1, A2. So source 1i is just one element, x, in this case. And dually, we have a unique pre-meet or just a meet. So y, this is y, we will use later. Okay. Then as we see, so we need some element which is outside of I. So here we have A1 prime, which is the source proper of I. And we need another element, which is called B1 prime, which is the sink of proper down I. Okay. Okay. Then we can input this information there, and we can write this matrix, the formula more explicitly. And if we have the representation, we have the persistent module M in this form, and then we can even insert the structured linear maps in this formula, and then by just computing the rank, the difference of ranks, we get the multiplicity. Okay, and again, because as you can see, our formula is not unique in a sense, because three blocks depend on the three choices. So you can change the choice. You can change your choice map. For example, in this case, you change your choice on the M3. So not A1, not A2B1, but A1B1. So they're the same, okay, because they are coincide with the DMVI. So you can always change a choice, but they have the same value. Okay. Okay, so keep this in mind. Okay, now after we're having this formula, explicit formula for interval multiplicity, so now let me introduce how we first generalize the rank invariant. So first, we need some notation called the compression systems. So first, again, let me just revisit the one parameter case. As we saw before, the rank 3-4 of the persistent homology M here is 2. How can we see that? Is that if you restrict your persistent module M or persistent homology M over 3-4, and you decompose this restriction, say M restrict on 3-4, you decompose it inside 3-4, inside this smaller poset, and multiplicity tells you the rank. Okay, so this is well-known fact. So this gives us a hint. So we can generalize the rank invariant in this by using the compression multiplicity. So we need compression systems. Okay, so what is a compression system? It is so for each interval I, we just assign such order preserving map from another poset xc to P, satisfying the following two conditions, which is very easy to describe. The first condition, so such order preserving map should factor through the inclusion map I to P. This is equivalent to saying that the image of Ci is contained in I. And second condition is that, of course, the image Ci should contain the source and sink of I. Okay, that's all. So the compression system satisfies these two conditions. And moreover, such compression system is called the rank compression system if the following one more condition is satisfied. So if for every segment I, xy, you can always find a morphism, a unique morphisms in xc with, from x, x prime to y prime, right? X prime smaller than y prime, such that Ci send x prime to x and send y prime to y. Okay, that's all. So later I will explain why we call this a rank compression system, why this condition 3 is important, and this is also related to our my last content with the called essential cover. Okay, great. So here I also give some canonical example of compression system. So the trivial example, of course, you can take xc to be I itself. So this gives you a trivial compression system, which we call the total compression system. And you have another choice. So this is also a trivial. So you just take the source and sink of I to be xc. So this and the inclusion map to be the order preserving map. So this again define a compression system, which we call the source and sink compression systems. But here I give a remark. So for these two compression systems, it automatically satisfies condition 3. So you can easily check that for each segment, if I is a segment, And by these definitions, it automatically satisfies 3. So total and source sink, they are automatically the rank comparing system. So let me give another comparing systems, which is not rank comparing systems. So here I give this W-shaped comparing system as follow. It has 5 vertex, 1, 2, 3, 4, 5, and we have this mapping. We have this table of mapping. Okay. So this defines an order-preserving maps which satisfy 1 and 2, but does not satisfy 3. So notice that this is not the rank comparing systems. Okay. Okay, great. So now we can define the interval rank invariant. So keep this commutative diagram in mind. I don't want to spend a lot of time on these diagrams, but you can think that, okay, so from the poset level, we go to the module level, and we can define the restriction functor, and everything is carried to another category, another category of module category, mod KXC. Okay, and you do the decomposition over there. Okay. Okay, then we can define the compression multiplicity as we want. So the compression multiplicity is nothing but just the multiplicity of the restriction. Okay. And we connect all the family of the compression multiplicity, and we call it the compression multiplicity invariant for all the intervals. Okay. And furthermore, if C is a rank compression system, so then we call the complete multiplicity the rank invariant or I rank. And the family is called now become the interval rank invariant under C. Okay. So you might ask, so why when it satisfies 3, we call it rank invariant, interval rank invariant. So this is because of the following proposition. If C is any compression system, so we can easily show that the compression multiplicity is, of course, is greater than the normal, the classical rank invariant. I mean, because now we only focus on segment in this proposition, so X and Y. So then rank, of course, we can define the rank invariant. Okay, and we say that we claim that this equality holds if C is a rank compression system. So this is why we give that such name. So because if C is a rank compression system, and if the restriction, the CMC restricted on the segment coincide with the rank invariant. So then this compression multiplicity can be extended to any, because we already extended to any finite, to any intervals. So then this is a natural generalization of the rank invariant. So then we give a name as an interval rank invariant, okay, by this proposition. And because, again, by the benefit of our formula, because it is defined as compression multiplicity, we have the formula for interval multiplicity. So we also have the formula for computing this compression multiplicity. But now, because things become simpler, because everything you restrict on IXC, so there's no information outside of IXC, because everything, the interval, the poset P is IXC, and we consider the full interval IXC, right? So there's nothing else outside of IXC. So now the formula only have the 4 blocks and 3 non-zero blocks. Okay. So this is the theorem. We also can compute the interval rank invariant by our formula. Okay, so now I want to go to our next main result, which is called essential cover. So first, let me just review the formula. So again, this is the formula again of the previous example. So here, as you can see, I label the M, the module M, as blue in blue. So actually, you can change the process. You can change the module M in this formula. So actually, the persistent module M is not essential in this formula. So what is essential in this formula? So if on the right hand side, if you can see that for this multiplicity matrix, if we put this persistent module outside of this matrix, and so it seems that it looks something like M, the persistent module M, act on some matrix, and this matrix, the entries are some morphisms of poset in a sense. So that matrix, the new matrix, only use the information of poset, not use any information of module. So we think this is more essential information in this formula. So this gives us our idea of essential cover later. Okay, so now let us just formalize this idea. So here we use some language by Gabriel. So we call it just formative how. I mean, we call such matrix using entries in poset P by the formative how. So actually, this is quite technical, but you can forget about this terminology. So you just think, okay, so we describe such morphisms with entries in P. As some morphisms in the formative how of the incidence category. So of course, let's just forget about this terminology. But we call later just the morphisms in this direct sum of Kp. Okay, just remember this is enough. And then we can say that so M act on this G. So that is how we express this the multiplicity matrix now. You can think in this way. Okay, so in some sense we take M outside of G. Okay, so now we restate theorem 1. So theorem 1 state that, okay, so choose any choice map C and D and any choice BA in source I times source sink I times source I. And then there always exist such morphisms in formative how of P such that this formula hold. Okay, this is just a restatement, nothing new. But this is important for introducing the essential cover. So now we want to, as we can see, so some information of morphisms in P is redundant or is not necessary to compute the interval multiplicity. So we want to find some more essential morphisms or essential, so we want some essential poset which can compute the interval multiplicity. So this is the idea. So to achieve this idea, so first we take some order preserving map zeta, say from Z to P. And again, this is formalization. So for this order preserving map, we can do the linearization. So it induce some functor from Kz to Kp, okay, of course. And you can, again, induce some functor from my additive how of Z to additive how of P, okay, nothing new. So it just sends the matrix to another matrix, okay, accordingly, yeah. Okay, so now we define the essential cover. So we call order preserving map zeta essential covers an interval I in P if satisfy the following two conditions. First condition, as you already seen in the restatement, so if there exists such G satisfies this formula hold, okay? So this condition always satisfied, okay, by the previous restatement. So the most important condition is the second one. If you can find another morphisms in Z, in formative of Z, such that this induced functor send this matrix to G. Okay, so then we call such order preserving map the essential cover. Okay, and our next theorem says, okay, so if zeta essential covers I, then you compute the interval multiplicity over P, and you compute the interval multiplicity over Z now, because R is a restraint functor from P to Z, mod Kp to mod Z, they are coincide. Okay, so then if we take Z as some smaller or more essential poset, so of P, or it can be totally different, I mean, independent of P, but we compute both interval multiplicity, they should coincide. So this is our main theorem 3 that tells you. And of course, because rank invariant and interval rank invariant or compression multiplicity invariant, they define as some special interval multiplicity. So it also can share this nice theorem. So we also have this theorem for the rank invariants, interval rank invariants. Okay. So as a quick example, first, again, this is an example of previous example. For this poset P and this interval I, you can take and we know the multiplicity matrix, of course, the G as I plot here. So now we can construct this special zigzag poset Z. And we can by verifying these two conditions, of course, we can easily see that, okay, so Z this order preserving map Z to P essentially covers I. Then it means that you compute the interval multiplicity over P is it's equivalent to do the similar thing in you compute the interval multiplicity over Z. Okay. Okay, so then we see another example, a filtration example. So for example, we compute this red region, this interval, considered as an interval. What is the first interval multiplicity of this region? And by the previous slide, we know that, okay, so you should take this zigzag poset Z, and you restrict everything. You just restrict everything over this zigzag poset. And then you compute, because we have a very nice fast algorithm to compute the zigzag persistent homology. You just decompose it, and you find how many full interval, namely everywhere is k, and you compute, and you find the multiplicity of that. So that multiplicity tells you the multiplicity of the original interval in your original filtration. And of course, you can do the similar thing for computing the I rank. But in this case, because as I explained, everything is restrict over I itself. So no other information outside of I. So in this case, so you can easily take this zigzag path. So we call the ZZI. So you can also show that, okay, so this ZZI to G52 essentially covers I relative to total comprehensive systems. So yeah, also easy. And you might notice that, okay, so again, so such Kasi is indeed a comprehensive system, and we have this coincide, the rank I over under tot and equal to rank I under ZZ. Okay, and if you notice that, okay, so it is already known that by Chamber and Nestor in 2018, so that the total rank invariant, the total rank is nothing but just a rank of limit to colimit. Okay, and by Ujing and by Kim and memory, on the right hand side, the rank of the limit colimit is known as the generalized rank invariant. So this formula, of course, is great. It's a bridge, which on the left-hand side, as you can see already, so left-hand side is defined as a multiplicity, is some algebraic object. But on the right-hand side, it is only use a category theory, so like limit and colimit. But they connected these two concepts together. So our essential cover also can cover the previous result of Day-Kim memory, that they also can find some zigzag path or zigzag poset, which says that, okay, so you compute the limit colimit of that the rank of limit colimit over that poset, that also gives you a generalized rank invariant. Okay, great. So I think I do not have enough time. So I think the last slide is most about another generalization of we generalize the multiplicity. Now we generalize multiplicity. So we just analog to doing the Mobius inversion formula of rank invariance. We can also do this for our compression multiplicity, and then it gives some sign interval multiplicity, and we formalize it, and then we call it interval replacement. So I think I do not have enough time to explain this part, but so this gives you another concise invariant or expressions which you can use to distinguish the filtrations. And our last theorem said that, okay, so the rank invariant, so this interval replacement preserve the interval rank invariant or the compression multiplicities. So it will not lose any information of rank invariant. Okay, okay, that's all. Thank you very much for your attention. Yeah.
Thank you very much for the great talk. Let's all unmute ourselves so that we can clap together for Enhao.
Yeah, thank you.
I think Zoom actually manages to cancel out the noise of the clapping, so it doesn't sound like clapping,
Oh,
but we are clapping.
okay. I see.
Who has a question for Enhao? Otherwise, I might just start with one. Yeah, then I'll go ahead. You had actually the very last slide. I think I would have the one that you had to rush through because there was not enough time.
Yes.
I
Yes,
think that
yes.
would have been answering the
Mhm.
question that I had the whole time kind of on my mind
Yes.
because
Mhm.
yeah, maybe you can pull up the slide again.
Oh, okay, okay. I will put up slide. Yes.
Because somehow the question that I had was
Mhm.
there's a lot of notation and a lot of it's easy to get lost in all of that,
Yeah,
but
sure. Yeah.
it's then hard for me to see what the intuition behind the objects is that you're defining. And so I think this last slide would have a bit more of the intuition.
Yes. Okay. So now let me just reshare the slide again. Okay. So can you see the slide now? Oh, sorry.
Not yet.
Oh, not yet. Yes. And how about now?
Yeah.
Okay, great. So, oh wait. Yes, so actually you can ignore so many notations because this page is quite dense. But as I said, the idea is now this interval replacement or sign interval multiplicity is just a generalization of interval multiplicity. So namely, so interval multiplicity is a real is a real multiplicity in a sense the multiplicity of interval summand of a given persistent module, right? So in that sense, the interval multiplicity is always non-negative. Okay.
Yeah.
Yes, but so we want to because we already generalize the rank invariant. Okay, and we have the relation. I mean, as we see in one parameter case. So the interval multiplicity and rank invariant they can recover both each of other by the namely the Mobius inversion formula. So. So if we already generalize the rank invariant by namely the compression multiplicity or interval rank invariant, okay, and then we're doing the same things for we're doing the Mobius inversion formula and we're doing alternative sum of interval rank invariant. It should give you another invariant, right? So this we call this the sign interval multiplicity. So here in this slide, it's just a delta MCI, right? So it's just alternative sum. You can forget many notations, but it's just alternative sum of the interval rank invariant or compression multiplicity invariant. So, but the point is here, sign interval multiplicity, this number can be negative. So it means it is not the real, the interval multiplicity. It's not really the multiplicity of interval I. So then, for example, if the persistent module or the persistent homology multiparameter, that is not interval decomposable, and it has no interval summand, for example, then of course, DMI is just zero. But delta MCI can be a non-zero value. For example, can be, in that case, it's negative. Yeah. So, and then we can use, so you see, so interval multiplicity is not very suitable for distinguish persistent module because if unluckily, so if M and N, they are both not interval decomposable and just, for example, indecomposables, which is not isomorphic to interval module. And then all the interval multiplicity are zero. So you cannot distinguish by using the interval multiplicity, of course. So, but you can distinguish by using the sign interval multiplicity. So this is the main things I think I want to share here. Interval replacement, so here is just a formalization. So you can forget about many terms like what is a split Grothendieck groups. So you think, okay, so we replace any module, any persistent module by a pair of interval decomposable modules, which we denote by plus and minus, which plus minus is determined by their sign multiplicity of each interval. And you just place, okay, so if the sign multiplicity is positive, okay, you place in plus part, and if it is negative, you place to a negative part. That's all. You forget about any terminology. That's all. You just replace it. So as I show the last the illustration for these two. If we want to distinguish these two filtration, which looks very similar, only the last, the maximum filtration is different. The maximum, the complex is different. And also, if you look at their persistent module, it also looks very similar. Only the one entry from changes, right? From 1 to 0 or from 0 to 1. But you can compute the interval replacement. So for M1, you can see that, okay, so it has four summand of positive part and one summand of negative part. So it has a negative part. But for M2, there is no negative part. Okay, so it's purely positive part. So by this, you can say, okay, because this is invariant, okay, so it can distinguish this by looking at the replacement. Yes.
Wow, that was exactly the answer I wanted to hear. That was so helpful. Thank you.
Thank you. Yeah, thank you very much. Yeah.
And so does it mean that you can distinguish
Yes.
filtrations more finely than all other methods or some other methods? Or like,
Yes.
can you explain a bit, like, compared to which methods can you distinguish more finely?
I don't understand. So what method? Well, what do you mean by method? Other methods? For example, if you
So
can give me some example, for example, yes.
other
Ranking invariant, for
invariants
example?
of multi-parameter persistence?
Yeah, sure. For example, the most well-known and most fundamental ranking invariant, right? So I think in this example, the ranking invariant are the same. I think
Yeah.
so. Yeah. So
So
you
you
cannot
can
distinguish, right?
distinguish
You cannot
better than the
distinguish.
rank invariant.
Yes, right. But ranking error, of course, we know this is in some sense very poor in some sense. So yes, of course. So this is one example. Yeah, yeah.
Great.
Mm.
Any other questions?
Yeah. So thanks for the talk.
Yeah.
Should I raise my hand? I don't know.
Yes.
Go for it.
So are you trying to build, like I've been trying to understand, try to build resolutions of modules by, let's say, these interval modules, and
Yes.
then your invariant.
Mm-hmm.
I mean, even the choices, right? You try to understand Euler characteristic of that resolution or number of,
Yes.
you know, the relative beta zero.
Yes. Yes.
Would be the number of exactly of these intercomposables.
Yes. Right.
And I mean, typically these resolutions are easier when the underlying poset is, let's say, lattice,
Yes.
distributive lattice, but you actually can do it for arbitrary posets.
Yes.
Right? Because these examples, like, you know, the examples when you put for the, you know, for this 2 times 4 or 2 times 5, those were lattices.
Yes,
so
right.
it's much, you know, things becomes much easier, even relative resolution by these
yes, right. Yes, I understand what you mean.
Interval modules.
Yes, yes.
But I think like interesting cases would be the cases where the underlying poset is not.
Yeah, right. Okay, so thanks for this very good point and good questions. First of all, yes, we consider any general poset, of course. So in our paper, you can find that actually we also give a projective presentation of interval modules. So in a sense, only 2 projectives in that resolution. But yeah, because that is enough for, I mean, by using oscillator Latin theory, that is enough to deduce this formula. But I think it's possible to also induce or get the projective presentation, not minimal maybe, but projective presentation for any interval vi. I think it should not be difficult because our in our paper we already give the projective presentation
Exactly.
of vi. So you see, so if so p is not lattice, so this is why we introduce the source or the minimum element, not the minimum element, right? So that is yeah. So in a sense, because the point is to show this formula, to have this formula, the minimality of projective presentation is not important. So even you have the projective presentation, interval module, you can still get the formula.
Yes,
but
yes,
maybe
and
you have
minimality
redundant
just
part.
gives you the best. Yes, yes, yes,
Yes, right,
so,
right, right.
Yeah, exactly. So we don't need to, we don't care about minimality.
Yes.
As long
right,
as it's still reasonable. Exactly.
Yeah, yeah. Sorry, what did you say?
You know, minimality is, you know, we often want minimality because it's like the smallest.
Yeah,
but
yeah, right. Or
minimality
unique,
you can give up still as long as this presentation is still reasonable size.
Yes, right. Yeah. So first, answer your question is that I think we can generalize even for any finite poset to get their projective resolution of interval modules, of course. And your second question is about I think like relative Betti numbers or like the Euler characters, right? So that is about relative homology or homology algebra. So this is more related to, first of all, the first author, the Professor Asashiba, Hideto Asashiba, his work, interval resolution, and also the Koshido complexes, co-resolutions, right? So, let me just return to that page. So this is why I introduce these component systems. Maybe many people already know this, but let me just review this one. So at the last, I introduced this W-shaped component systems, this W-shape, which is not the ranking component systems. So in Professor Asashiba and other co-authors, their previous work, they built some nice connection between interval replacement using this spatial component systems and to recover or to compute the interval resolution, the so-called interval resolution. That is, you use some homological algebra things to define the approximation, the right approximation or left approximation. You get some resolution, relative resolution relative to interval modules. So now not only projective incompossibles, but now you also consider all the interval incompossibles. That is called the relative version. Yes, so for this, so this is known that now it's known that using TOT or SS, you cannot get this nice connection with this relative homology. Only for ladder case, only two rows, of course. Only use this W shape, spatial W shape one. You can get this very nice connection with relative homology. So then you can then distinguish modules by looking at their resolutions. This is very strong than by looking at their invariants. Yes. So I'm also now working on some part of this works recently. Yes. I hope I answer your question. Thank you.
Yes. Thank you.
Thank you. Yeah.
Thank you. That's great. If we don't have any last short questions, then I would end the recording here. Does anyone have a short question? Okay, people can anyway also ask questions after the recording is over. So let me thank you again for the great talk.
Thank you very much. Thank you for listening. Yeah.